Have discussed greenhouse gas removals, mostly carbon dioxide removal, and what scales they're at now and how they need to scale up if we are to really rely on them for being part of the solution to meet global warming targets like 1.5 degrees C, 2 degrees C, and so on by 2100. This is a report from Bezos Earth Fund. We have read another report from this group before. Scaling technological greenhouse gas removal, a global roadmap to 2050. A detailed meta-analysis that I'm going to briefly read just because it's a very important topic and some of it is kind of a re-emphasis of what we have already talked about. With our climate at a tipping point, technological greenhouse gas removals has emerged as a new frontier in the solution space. This report represents a roadmap of actions needed to scale up greenhouse gas removal by 2050. Okay, so we already know that removing them can be, if we start sucking down greenhouse gases, then people may think, well, we can continue to emit because anyway we're taking them out. So the moral hazard exists, plus it's unlikely that we're going to scale up to a level that will make this possible in any case. And are we relying too much on it right now in terms of our future mitigation plans, global warming targets, etc.? These are all nice questions, but here we'll come back to just two reasons why this will be a main challenge. Technological greenhouse gas removal, GHGR, must achieve a massive scale. So if we have to be realistic in terms of solutions, we need to go up to about 10 gigaton CO2 per year by 2050. Obviously, that means we already need to include greenhouse gases and think about CO2 equivalent and not just CO2, because otherwise our net zero and every other target is going to be off track. Technological GHGR must scale on a short time frame, so these things have to happen pretty rapidly because we are not bending the curve yet. We are happily chugging along. You are increasing renewable deployment, electric vehicles, lots of good things are happening, efforts to decarbonize steel and carbon industries, etc. But the emissions curve is not bending yet. So this has to happen very, very quickly to deal with all those sorts of issues. How this roadmap is different from what you have seen before: it's global rather than national or regional. It is inclusive of the broad range of stakeholders and actions required, including socio-behavioral and communities and finance and markets and policy and regulations, alongside science and technical issues. So it is a very detailed report. I'm obviously jumping ahead with the text, as you can see. I'm not reading everything. This report includes methane and nitrous oxide removal in addition to carbon dioxide removal, focuses on technological rather than nature-based greenhouse gas removals, excludes approaches that reduce emissions. So it's not about efficiency and emissions reductions, it's about removing greenhouse gases, and it sets a specific goal for CDR in 2050, that is carbon dioxide removal, not greenhouse gas removal. The path forward is shared through multiple perspectives across this roadmap. There are sections on thematic areas for stakeholder engagement that describe how various stakeholders can get involved, and there are also technology roadmap initiatives for describing what is needed in different technical areas. And at the highest level, section 8 tells a story of what actions are required to achieve the overall goal of the roadmap. So it's a timeline view of the roadmap content, and it's described through 3 decadal periods. We'll look at how this is going to play out, but here is a figure to kind of give you a sense. Roadmap for scaling technological greenhouse gas removal by 2050. This is an abridged version, and I am abridging the whole report anyways. The initiatives range from R&D, deployment, community engagement, social science to public engagement, workforce, infrastructure, permitting, financing, standards setting, market infrastructure, demand, and field building. So there are various steps. Emergence, so 2020s, we are in the middle now. I'm recording this in 2025, April, end of March actually. It's March 31st. Yeah. So 2030s adoption and 2040s expansion. So you can see greenhouse gas removal in gigatons per year has to keep ramping up, and this is the timeline here. Of course, there are technology search, incubation and testing, and regulatory standards for safety and monitoring, reporting and verification, market infrastructure development, voluntary purchases and frameworks for procurement, etc. Field building, what does it mean? Continued field building for greenhouse gas removal, including convenings, working groups, communities of practice and regular efforts to update the goals of the field. The field is, of course, greenhouse gas removal as a whole. Adoption, technology adoption and prioritization, global monitoring, reporting and verification, certifying, publicly managing procurements, and expansion, of course, means technology scaling, global implementation. Exactly what mechanisms will work? Will it be market mechanisms? Will it be international negotiations? Unclear. Just deployments in new communities, global coalition building, workforce scaling. So there is a lot of discussion elsewhere on how mitigation in whatever form, including greenhouse gas removals, have to be equitable and just. It cannot again start hammering low income and middle income countries, because they are paying a huge price because of cumulative carbon created by the rich countries. Now we start to remove them. What are the impacts? We don't know that yet clearly. Okay, if we scale up to removing 10 gigatons of CO2 equivalent, let's say, per year, what will it mean for the climate? And locally, what will it mean in terms of climate risks? All those issues are still out there. And of course, how it will be implemented, who gets the benefits, etc. Removal of greenhouse gases is critical to achieving long-term goals, so the motivation is hardly needed, but let's look at it anyway. The gross emissions going from 2000s, we are expecting to peak somewhere. We haven't peaked yet, but we have to start dropping, and then at some point removal is needed to excess emissions out to remove excess emissions out of the environment. Basically, there will be irreducible emissions, and we will make it net negative by basically taking out more than we are emitting. All this to meet the 2 degree C warming target by 67% probability by 2100, let's say, because 1.5 looks quite impossible at this point. But if we are very successful at taking out greenhouse gases, then maybe we'll start bending the warming trend as well. Okay, critical but out of the scope of this report, fossil fuel phase out. So there are other constructions in reducing other constraints like reducing deforestation, electrification, but the focus here is really greenhouse gas removal, including carbon dioxide, methane, nitrous oxide, and any other non-CO2 greenhouse gas. Okay, scope of greenhouse gas removal technology approaches included in this roadmap. So approaches in blue belong to in more than one category. They are bolded in their primary categories. So you have scope, so in scope and out of scope is the categorization. CDR from the air, from the ocean, from land, from rock, and non-CO2 greenhouse gas emissions like N2O and CH4. So we have talked about this elsewhere, direct air capture and electrochemical CO2 removal. This is in scope, but I'm not going to go into details here. Point source carbon capture and sequestration is out of scope of this report. CDR ocean is in scope. Land and living biomass approaches such as management, conservation and restoration of forest, agricultural, so nature-based solutions in general are not included here. And point sources of methane and N2O are also not included. Important ways in which non-CO2 greenhouse gas removal differs from CDR itself. What are the challenges? Potency, methane is 120 times and nitrous oxide is 270 3 times more potent. Concentrations, they are higher, of course. CO2 is very small, 0.04%. Residence time of methane is order 12 years, but N2O is 110 years, whereas CO2 has got a residence time of multiple centuries. Sources, of course, there are direct and indirect, natural and human, and so on. Complexity, sources and sinks of methane and nitrous oxide are connected. These gases also interact with other greenhouse gases in the atmosphere. Methane is highly oxidizable, converts to CO2 and water, and so on. Technology maturity, CDR includes approaches with medium to high technical readiness level, whereas non-CO2 greenhouse gas removal approaches are very low at TRL level 2 or below. Approach, where CDR removes CO2 from the atmosphere, non-CO2 greenhouse gas removal typically seeks to convert the non-CO2 gas into a molecule with lower warming potential, such as the oxidation of methane into CO2. So if methane is 120 times more potent, this depends actually on how you do this, by kilogram or molecular level, etc. So you have to be careful with these numbers. We often say methane is 25 times as powerful as CO2, but here you see the number is 120, so you have to make sure that we are using the right numbers. But nonetheless, converting methane to CO2 does reduce the global warming potential, even though you don't take it out necessarily. Roadmap goal for technological greenhouse gas removal: CDR reach 10 gigaton CO2 per year of durable technological removals by 2050. Non-CO2 greenhouse gases advance the science of non-CO2 removal such that decisions can be made by the early 2030s about future development and deployment, and these goals may change as the science gets better. How can we think about it? Put the scale of global removal challenge into perspective. The largest global commodities in gigatons per year, coal is the big monster here, and then you have cement and iron ore, oil and gas, etc. And you think about global waste production in 2023, this is also in 2023 in gigatons per year. Global municipal solid waste was 2.1 gigatons, and global CO2 emission was 41 gigaton in 2023. It jumped up after COVID, but also this is not CO2 equivalent, which will jump it up further towards 50 gigaton CO2 equivalent per year. What we need: future global technological carbon dioxide removal requirements in gigaton CO2 per year. Then by 2030 we need to be at 0.285. By 2040 we need to ramp it up to 4.5. By 2050 we need to be order 10 gigaton CO2 per year. Okay. Hypothetical CDR deployment trajectory that takes the shape of an S-curve here. Removal in gigaton CO2 per year going from 2030 0.285, 4.5, 10, which we already said. We call this typically the S-curve. You plateau out at some point. Looking at the critical roles for greenhouse gas removal stakeholder groups across 4 thematic areas. I won't read, it's a very detailed table. Stakeholder groups, though: companies that purchase or supply CDR, funders, greenhouse gas removal communities, government actors, journalists and media, non-profit and civil society organizations and researchers. And you have more details in each one of them. What are the themes? Science and technology, socio-behavioral and communities. This is interesting that this is included here, and it's very important, of course, because social-technical transitions are always tricky. Finance and markets, policy and regulation. Okay, let's read top one in each one of them. In science and technology, we have innovate, develop and implement GHGR approaches and share data. For researchers, that will be about developing GHGR technologies, models and GHGR hardware that scale, and conduct basic and applied research. Socio-behavioral, involve communities early and meaningfully and provide co-benefits. So co-developing these solutions is critical for making sure that they get taken up. And here at the bottom, research community, social and cultural context for deployment of the GHGR technologies. Finance and markets uncover funding gaps, advance the most promising market infrastructure to ensure that it becomes self-sustained and not just subsidized somehow in a very uneconomic way. Policy and regulations, iterative deployment informs standards and regulations, and at the bottom, use research to inform place-based standards and regulations. I'm skipping because they are useful, but they are a lot. You have to go back and read. I cannot theoretically include such details in such a brief introduction anyways. The report is available. Please go read it if you are interested in the details. Current cost and technology readiness level of 5 major GHGR areas. TRL of most established: air CDR 3 to 9, ocean CDR 4 to 7, land CDR 5 to 9, rock CDR 6 to 7, non-CO2 GHGR down at 1 to 2. I've discussed these elsewhere, so I won't go into the details of what they mean. Cost per ton of CO2 is always critical because otherwise it doesn't get it become part of the market mechanism, market dynamics. 600 to 1200 per ton of CO2. This has to come under 200 for it to be viable as a basic approach climate solution, part of the climate solution. Ocean CDR 100 to 1300 per ton of CO2, land CDR 100 to 500 per ton of CO2, and rock CDR is at 100 to 400 per ton of CO2. We don't know what it is for non-CO2 GHGR removal yet. So these are estimates from last year, but obviously these will keep changing. Technology keeps moving forward. Research priorities. So I'll just jump ahead and start reading some research priorities for the various approaches. I'm expecting a delivery, so I keep peeking out of the window. Material, so for CDR, materials breakthroughs, process energy efficiency, design and feasibility improvements, novel scalable approaches, process integration including co-location with heat sources to reduce electricity demand. So in a life cycle sense, you want to optimize everything. Improved monitoring and verification of removals including accounting mechanisms, improved understanding of the impacts, benefits, risks and costs. Biggest barriers: ocean system science itself, monitoring, reporting, verification. If somebody is claiming out in the middle of the ocean they are doing something, you need to show additionality, that you are actually putting out more CO2 than naturally would occur anyways. Deployment and monitoring hardware, potential environmental impacts, and legal frameworks to use international waters to do these things. Biggest barriers facing land CDR: sustainable biomass, so it's not easy to do these things, especially if you are competing for water and land with other basic subsistence grains and so on. Durability: how long will it remain? Open systems measurements, life cycle analysis, and monitoring, reporting, verification, development. I'm being supremely brief, but you get the point I'm trying to make. Biggest barriers for rock CDR: impacts on human health and environment. So obviously often there is breaking down of the rocks into powder to transport them and increase their surface area to volume, so weathering is accelerated, but you also add alkalinity, metal leaching and other environmental concerns. Modeling and measurement, of course. Mineralization rates: we are assuming that CO2 removal will be sustained, but how will it actually work in reality? So measurement of mineralizations and weathering are going to be tricky. Feedstock inventory, of course, olivine, other material that you're going to use, crush and then transport. So life cycle analysis is again needed. Biggest barriers facing non-CO2 greenhouse gas removal: understanding of atmospheric systems, removal technologies themselves, unintended consequences, always important, quantification of different removals. Okay, so finally, a roadmap for scaling technological greenhouse removals by 2050. We already said 0.285 gigaton CO2 per year to 10 gigaton CO2 per year from 2030 to 2050, and level of relevance for key stakeholder groups: science, technology, policy, regulation, finance and markets, socio-behavioral and communities. So you have a scale here associated with the feasibilities, let's say high, medium and low. And here you have emergence, adoption, and expansion, as we said, up to 2030, 40, and 50 respectively. R&D, allocating budgets, reducing cost per ton of CO2 removal, advancing scale of incubation, and so on over time. And example initiatives, ocean CDR, air CDR, non-CO2 GHGR, non-CO2 GHGR initiative has several. So these are already being tried. This is a big market, according to the people who hedge bets on investments on technologies, and obviously they are putting lots of money into this. So deployment will need demonstration projects, commercial deployment, and global implementation over time. And there are examples again in ocean CDR, land CDR, and rock CDR that have already happened. Community engagement, co-design has to happen, community playbooks, and just deployments in new communities. Examples of initiatives for specific GHGR technologies: air CDR initiative exists, ocean CDR initiative. So meaningfully involve communities in initial siting and project design process for 100% of field trials and demos. So these are the timelines they are imagining. So these are kind of projections and what they think is needed for scaling up greenhouse gas removals by 2050 to order 10 gigaton CO2 per year. Social science is of course needed. We have to study CDR impacts, risks, perceptions, and scalability, public engagement, workforce training, infrastructure needs to be in place. Permitting, of course, permitting structures and agile permitting structures as well to respond to how technology develops, how markets develop, how communities accept and live with it, what the unintended consequences are, and so on and so forth. Financing, of course, government-backed capex in the beginning, but commercial capex in the 2030s, and then private financing at scale in the 2040s. Well, good dream. Let's hope it works out that way. Standard setting, of course, and market infrastructure. Market infrastructure development, certified markets have to evolve by 2030, and demand from carbon markets, 40 to 60 billion per year of CDR credits expected in the 2030s, and publicly mandated procurement of 4.5 gigaton CO2 per year by 2030s, and then 10 gigaton CO2 per year by 2040s. Field building throughout the period, continued field building for GHGR, including convenings, working groups, trade organizations, and regular efforts to update the goals and approach of the field. Okay, so I obviously run through it, but you get a sense that a lot of attention has been given to details in this report commissioned by the Bezos Earth, what is it called? Bezos Earth Fund. So Eric Schmidt and Jeff Bezos and others are putting money into these technologies. It's at a level that should create disruptions. Are they really doing a good thing? You know, the debate goes on about Bill Gates funding lots of health work, and not all health researchers and workers are happy in the way things are done, but that's not going to stop Bill Gates and Melinda Gates from doing what they are doing. Similarly, Eric Schmidt and Jeff Bezos are putting money into various of these technologies and research, and we just have to hope that everything is synergistic for global warming targets and generally bending the curve, bringing the emissions down, doing it in an equitable and just manner across the world, right? So let's hope that's how it works out. Okay, so I'm going to leave it here.